cannot heal the crack and the component, so everybody knows we have to predict the lifetime. And we can do that in fracture mechanics by using driving force terms. And this driving force term should allow the prediction of the growth rate of fatigue rates. And everybody knows how to assess the fatigue rate growth rate with the stress intensity range or the effective stress intensity range. If linear elastic fracture mechanics is valid, it means that the crack tip plastic zone is limited to the region very close to the crack tip. And here you just have to insert the okay. Here you just have to insert the mathematical comparison operator significantly larger. So the requirement is that the plastic zone size is significantly larger than the crack length for the uncracked ligament. But when the load is high, then we know the plastic zone size increases, and then delta K concept is not applicable anymore. The same applies when we have short fatigue cracks, since then it is very hard to meet the condition that the plastic zone size is significantly smaller than the crack length. Furthermore, load fluctuations provide additional difficulties for the assessment of the fatigue crack rate. And for example, when we consider low cyclic fatigue, everybody knows up to now the cyclic chain decay from the regime of the elastic fracture mechanics has been applied. But about J theory, we have to bear in mind that the classical chain decay approach is based on the assumption of deformation theory of plasticity. This means that the real elastic plastic material is idealized to behave like a nonlinear elastic material, and this means that in this theory the total strain energy density is assumed to be fully reversible, although in a real elastic plastic material only the elastic part of the strain energy density is fully recoverable after loading. And this assumption leads now to the fact that the conventional chain decay does not deliver a true thermodynamic driving force term in elastic plastic materials, and therefore also the physical meaning of a delta chain decay remains unclear. Another point is that deformation plasticity is not applicable for cyclic loading and crack extension, and the reason is that when we have unloading, we reach different points here, so different strains are predicted with deformation theory. And therefore, this fact casts doubts on the general application of the delta J approach. About I have here two quantities here. I have only to say that delta J convention means the theoretical chain decay that has been introduced by Tanaka, for example, or by Ludwig, and delta J experimental is the famous cyclic chain decay introduced by Dowling and Berger. And this quantity can be easily determined from the area below the load displacement record of a fatigue test. So, although we have here these two problems, everybody knows that experiments show that the experimental cyclic chain decay correlates in some cases very close to the fatigue record rate. And we know also that this quantity gives the same result as the theoretical delta chain decay. But up to now, there was no real proof if the conventional delta J approach is really correct. In order to overcome now the problems that are related to the assumption of deformation plasticity and that lead to the fundamental problems of the conventional chain decay, we have to use incremental theory of plasticity, which gives us the correct mathematical description of real elastic plastic materials. And the configurational force concept enables us now to derive a new type of chain decay, which is called the elastic plastic chain decay with incremental theory of plasticity. And this new chain decay delivers now, in contrast to the conventional chain decay, parameter that has a true the physical meaning of a true thermodynamic driving force term in elastic plastic materials, and the elastic plastic chain integral is also applicable for cyclic loading in crack extension. However, one has to bear in mind that the elastic plastic chain integral is in general path dependent in elastic plastic materials, since bar configurational forces appear in plastically deformed regions. This means just that if I increase my integration contour, more and more configurational forces are included, and therefore the value of the chain integral changes. And therefore it is necessary to find out how should we use this new type of chain integral for the evaluation of a cyclic chain integral term, which reflects the true driving force of growing fatigue rates. In order to answer this question, we investigated the path dependence of the elastic plastic chain integral in numerical fraction mechanics tests with finite elements. We performed case studies for two-dimensional compact tension specimens made of elastic plastic material that follow incremental plasticity. Long cracks were considered that remain either stationary or grow under cyclic mode 1 loading conditions. And we considered also various load ratios from tension compression to pure tension loading. And the maximum load was varied in such a way that we received different yielding conditions, so different sizes of the plastic zone, from small scale yielding to large scale yielding and general yielding. After the stress and strain analysis with finite elements, we obtained the configurational forces at each node of the finite element mesh by a self-written post-processor based on the Müller's Professor Müller from Kaiserslautern. And the evaluation of the chain integral is then simply a summation of all the configurational forces that lie within the area bounded by the integration force. So the results show then that in order to calculate the driving force for growing fatigue crack, we have to calculate a cyclic chain integral term and consider an integration contour around the active plastic zone of around the moving crack tip. And this is clear when we think about fatigue crack extension. Only the active plastic zone travels, and cyclic plastic deformation around the moving crack tip is responsible for the fatigue crack extension process. And as a consequence of this cyclic plastic deformation, we can show, we know that the fatigue crack off rate is proportional to the change in the crack tip opening displacement between maximum and minimum loads during a specific load cycle. And by comparisons with the cyclic crack tip opening displacement, we can show that we have to compute a cyclic chain integral in general according to this equation. In order to be proportional to the cyclic crack tip opening displacement, as you can see here, and therefore to be proportional to the fatigue crack rate. Here we just have to insert the J values at maximum and minimum loads of a particular load cycle. And in the case of tension compression loading, J min becomes 0, and then we arrive finally at this simple equation. The results also show that the conventional cyclic chain integrals are only correct for the limiting case of stationary fatigue rate. The reason is that the conventional cyclic chain integrals give always the magnitude of an incremental plasticity cyclic chain integral, which is computed for our integration contour that encloses the entire crack tip plastic zone, which consists after fatigue crack extension beside the active plastic zone also of the plastic weight and the initial crack tip plastic zone that has been created after the first loading step. Only when we have no active crack extension, then the total crack tip plastic zone consists only of the active plastic zone, and then we have the correct value for the fatigue crack driving force. And the reason for the validity of this equation becomes clear from this picture. You can see here that the integration contour goes only through elastically deformed regions where the total strain energy density consists only of an elastic part, and therefore deformation and incremental theory of plasticity give the same values for changing curves. The best way to demonstrate now why the active plastic zone has to be considered in cyclic changing term can be demonstrated by considering numerical overload experiments. We all know that after application of a single tensile overload, fatigue breakgrowth retardation occurs, and this can be easily shown with finite elements by plotting the variations of the cyclic corrective opening displacement, which is even after an overload proportional to the fatigue breakgrowth rate. And here we can see that the conventional cyclic changing bars do not show the overload effect. And the reason is that when we look at the theoretical cyclic changing bar, before I mentioned, the integration path is only going through elastically deformed region, and in such regions we have no residual stresses which are responsible for the breakgrowth retardation phenomenon. On the contrary, the active plastic zone moves after application of a single tensile overload within this overload plastic zone where compressive residual stresses appear, and therefore the new parameter shows even the delayed retardation phenomenon and correlates perfectly with the variations of the cyclic corrective opening displacement. So this is really the numerical proof that this parameter is correct. So in order to find out now what makes the difference between the conventional cyclic changing bar and the new parameter, we can make a configurational force analysis. Here we can see the schematic sketch of the distribution of the configurational forces within the entire affected plastic zone. And if we bear in mind that only configurational forces that have a component in x direction, which is the direction into breakgrowth direction, deliver a contribution to the driving force, we see here that only the left side of the boundary of the initial corrective plastic zone and the initial corrective blunting region, that this region makes the difference between these two values. And the future aim is now what we want to find. We want to develop a correction factor which expresses now the influence of the initial corrective plastic zone. And we did already some numerical investigations what we, for zero tension cyclic coating and for different heating conditions. And what we found is that if the plastic zone size remains constant, also the correction factor or this difference between these two values remains constant. What we could also show is that crack extension has not really an influence on the difference, because this becomes clear also from the configurational force analysis. The configurational forces in the plastic case have only a component into vertical direction, but no component into breakgrowth direction. For the future, this is now done only for specific load ratio, and for the future we want to vary also the load ratio to find out what is the role now of the minimum load, and how does the cyclic plastic zone influence the difference between the conventional cyclic changing bar and the new parameter. So as a conclusion, I can conclude my talk now in just 2 points, that the incremental plasticity cyclic changing bar computed for integration contour that encloses the active plastic zone, the carbon corrective, characterizes the fatigue breakgrowth rate in elastic plastic materials in cases where the conventional delta K approach is not valid anymore. And we could see also that the new parameter is also able to accurately characterize the well-known delayed breakgrowth retardation phenomenon after single tensile overload. The application of the classical cyclic changing bars is not fully appropriate, especially when we have growing fatigue cracks, and one has to be even careful because this approach can lead to a non-conservative fatigue lifetime assessment of components, especially in the regime of local cyclic, they should be applied. And therefore, for the future, we want to develop a new, easy-to-use approach, which allows the determination of the correct or deep backdragging force, and which might replace the conventional experiment. Thank you very much.